Hi everyone, myself Ansh. This is my presentation for Lab 3 focused on digital sampling. My project explores engine sound analysis and how digital sampling allows us to better understand and optimize automotive acoustics. So, to start off, here are the 11 audio tracks we studied in lab. They helped us understand the spectral fingerprints of different waveforms. We identified sine, square, triangle, and sawtooth waves, each with unique frequency characteristics. While important background, this section is already verified and not central to the rest of the analysis. This is the next slide. So let's go to exploring automotive noise pollution. Let's shift focus to the core topic, automotive engine noise. In daily traffic or at motorsport venues, engine noise is a major contributor to environmental noise pollution. Most of the noise originates from the combustion cycle, exhaust, and airflow systems. So over the years, regulations and innovations like noise barriers, as you can see on the highway, um, has improved exhaust and have helped reduce this impact. So to accomplish this, I used the game engineering tool Automation to virtually build and test 6 engines. I kept the material and configuration consistent across all engines to ensure fair comparisons. So the 4 main engines that I tested were all 3-liter variants, V6, V8, V10, and V12. I also created additional V8 engines with different displacements, a compact 1.5 liter and a powerful 6 liter. Each engine was simulated running at 6000 RPM to replicate high load performance conditions. I recorded the audio in two ways. First, through a 3.5mm jack at 100% volume to capture digital signal output, and the second through a microphone placed near the speaker at 70% volume to replicate real-world acoustic recording. All the data was sampled at 22,000 samples per second with a total record length of 102 samples. The VRMS, the power values, essentially a measure of the signal strength, were used as a proxy for perceived loudness. So this slide shows the VRMS power levels for the 3-liter engines. As expected, the V10 and V12 engines produced more power acoustically than V6 and V8. This is primarily due to their greater number of combustion events per cycle and larger airflow volumes. Even though all engines were the same size in terms of displacement, the extra cylinders created more complex harmonic content and louder overall sounds. So, when capturing the actual sound through a microphone, the results were consistent. The V10 and V12 again register as louder, reinforcing the idea that more cylinders, even in the same volume, increase overall sound output. These findings suggest that the cylinder count, not just the engine displacement, plays a major role in how loud an engine sounds. This slide 9 shows how engine size also influences sound. The 6-liter V8 was significantly louder than the 3-liter and the 1.5-liter versions, despite the identical firing orders. Displacement clearly correlates with acoustic output. Slide 10 backs this up with the microphone data. The 6-liter V8 produced the most noise, followed by the 3-liter and then the compact 1.5-liter. This clearly shows the trade-off between the engine power and the acoustic footprint. One of the most fascinating patterns I noticed came from the harmonic peaks from across different engine types. Engines like the V6 and V12, despite differences in configuration, exhibited very similar peak frequencies. That's because they share a common ancestor, the inline-3 engine. This observation led to the concept of engine families. Engines are often scaled versions of simpler base configurations, like how the i3s build into V6 V12 or how i4s extend to V8 and V16. These family relationships explain why certain engines produce similar harmonic content. It's not random, it's built into their mechanical DNA. Using everything that I learned, I set out to design a quieter yet high-performing engine suitable for motorsports. I chose a 4.6-liter V8 for balance, that it gave me the power output I wanted without the excessive high-frequency noise of the 6-liter. So to further reduce sound, I added two reverse flow mufflers and a high flow three-way catalytic converter. The result was impressive. The engine produced 478 horsepower but was 20% quieter than the 3-liter V8 and 37.5% quieter than the 6-liter. It's important to note that many race cars run without mufflers, prioritizing power over comfort. But this experiment shows you can get both performance and acoustic control by carefully selecting displacement and optimizing the exhaust system. In conclusion, the loudness and the frequency profile of an engine depend heavily on its displacement and cylinder configuration. Engine families share harmonic characteristics which can be leveraged to design quieter engines. This is especially useful in applications like autocross, where engine performance matters but sound restrictions may still apply. And my references will be on next slide. This is my references section. Thank you for listening.